And the last part, we get really into the low level of things, is reverse engineering. So that is taking a compiled executable that's machine code, right? That's normally very difficult to work with. It's just binary. We can't read that. We're going to disassemble it, and we can potentially patch it so we can change the machine code. And in doing so, we can take a legitimate program, change the machine code, make it do something that we want it to do. And now it looks like the legitimate program, except say it might contact our server and send us your password, right? Or it might put a keylogger on your machine and send us everything you type at the keyboard. We can make a program do, in theory, whatever we want, but it could be a legitimate program we could change that way. We can also change operating system files that way. So a Trojan Horse is a changed program. Users think that it's something they want, but it does something that it shouldn't. And we can change an operating system file that way. And in doing that, our operating system itself will become infected. So we're going to take a look now at how to actually do reverse engineering, how to make Trojan horses, and how to potentially make rootkits if we do this on operating system files. Does anyone know what a rootkit is? No, Sarah?
Rooting, the root for like giving yourself authorization to edit all the files in the computer, like the operating system too, and the root.
Yeah. Yeah, so what Sarah said is that root is a type of privilege level, the highest one in Unix. It allows you to edit everything on the system, right? A rootkit runs in the root of the system. The root of the system is also the name for the main operating system files. So a root user has access to those. Most users don't. That's why it's called root, right? So a rootkit is malicious code that runs within the operating system files. So we can go ahead and change the operating system files to do what we want, even though they're compiled machine code, normally very difficult to work with. And in doing so, we can create a rootkit, right? So today I'm just going to show you sort of the basics for how the technique works. We won't actually be creating a rootkit. We won't actually be creating a Trojan horse because it's very, very difficult to do, right? Writing an assembly is hard enough. Writing a machine code is hard enough. Changing someone else's machine code is very difficult. So we will take a look at a program I've specifically written to make it possible to do in this class. And before we do that, we'll take a quick look at Trojan horses, right? So do you all know the story of the Trojan horse in history? Right? Anyone not? Okay. Yeah, so a Trojan horse is malware inside what looks like a good thing. And we can change a legitimate program to do what we want. And another thing we can do is crack it, right? So software that requires a password or buying a license to use, by using reverse engineering, it's actually possible to make that software work regardless. So that's something that most cracks out there that let you run illegal software, that's what they use to do it. So it takes very smart people to make illegal software, as we'll see. So let's try it. Open up your course folder. And you should see a secret.exe in there. Run it. It's going to ask you for a password. Right? And if you enter anything, the password will not work. The password is a rather unsecure password. It is all camel case, and it's also in your PowerPoint. Right? And it says, congrats, the secret is 42. Sorry? What's the secret is 42? Have you ever read The Hitchhiker's Guide to the Galaxy? Okay, it's a reference to that. Yeah, 42 is the answer to life, the universe, and everything. Yeah, they just don't know what the question is. Yeah, it's a good book. Yeah, oh yeah, it's hilarious. So we have we've entered the password, we've entered incorrect passwords. We see that the program works, right? Now this is just a simple secret it's protecting. It could be protecting something more valuable than that, right? So we press a key to end it. Let's take a look at the code that runs this software. So that code is secret.cpp. Open that with your favorite text editor. It's not very well written. I've written it specifically to make it easy to alter the code when it's in compiled form. right? So we see our character, it makes a string correct :F, right? This standard C out, we're going to ask, please enter the password. That's what you saw. And we're going to read from the standard input into entered, right? That's like Python print, and Python also has reading functions. So that's what we use for that. And it compares entered to the correct password. If that is the case, if they're equal, it's going to set C8 to true. So this is going to change its value to correct :T. Makes sense? Once we're done that, we're going to check if it is correct :T. If that's the case, we're going to print the password. Otherwise, we're going to ask for it again when the user enters 0. Then we're going to say better luck next time. Julian? Can you change the password? You kind of can. Yeah, you can change the password in the code and recompile it. And you can change the password in the compiled executable. You just have to do that at the machine code level, which we'll look at right now. Right? So this is the code that runs this program. What we're going to do is you should see a hexedit.exe in here. Okay? Take your secret.exe and drag it on top of hexedit.exe. If it gives you a security issue, just click Run. This is a binary editor. It's going to edit the binary of that file, right? So we see here, it's like that program we were looking at in our jib assembler, except this time it's x86 code, and it looks very similar, right? We have the memory space, and it says here this program can't be run in DOS mode. If we try to, it's going to print that. And what we have somewhere down the line is our correct :F string. Go ahead and go find and type correct :F. Make sure it's on ASCII. And go OK. And it's going to find it. Right? What we see here is we have correct :F. That's the ASCII equivalent inside. This is in the binary program. And F, capital F, corresponds to hexadecimal 46. We're going to select this F in the ASCII equivalent. Oops. And we're going to type capital T. Now that changes it from 46 to 54. That is the ASCII hexadecimal value for capital T. Sorry? So you're going to search for correct :F, or you can just search for correct. Oh, okay. You've got, okay. Some of you are opening secret.cpp in the hex editor. It's got to be secret.exe, right? We can change the C++ source code in any old file editor. We need to use this to change a binary executable. Okay? You guys all have it? Anyone still having trouble? So we've changed that to a capital T now. Now we're going to go File, Save As, and we can just call it secret2. So we've saved that. You should now, and you're going to have to save it somewhere other than the shared folder because you don't have access to the shared folder. You should now see a secret2.exe. For those of you who have gotten that far, when you run secret2.exe, enter any password, it will always give you the secret. I misspoke. It is secret2.exe. You have to add the .exe to the end when you save it.
.exe.
Ah, good question. That's a good question, so I'll say it to the class. So everyone, Julian asked a very good question. He asked, does every program have a C++ source? The answer is, in almost all cases, it has something similar. If it is a compiled program, if it is machine code, it'll have a language like C or Fortran, sometimes assembly, that you compile into the machine code. Some very early programs, people wrote direct machine code. People invented assembly very early on, so they didn't have to. So almost every binary program does have a source code in some kind of third-generation language. Yeah, almost always it's a text file. In cases like Python, Python's what's called interpreted. It doesn't actually compile to machine code. It just runs through the text and interprets the text as it's viewing that, so it runs the script directly. But the Python interpreter is machine code. Yes?
When do we use this?
When do we use what?
Like changing, bypassing this?
Okay. Richard, right? Yeah. So Richard asked a good question. When would we use this? So right now we just showed essentially how to bypass the password in a poorly written program, right? There are ways to write the program to counteract this. We could use this in any program that asks for a password to do something, right?
So we just change everything.
Pardon?
Just bypassing the password system?
Yeah.
Isn't that illegal?
It's not illegal because I wrote this program, so I'm telling you you can do what you want with it.
But we can't do it with like actual.
Yes. Yeah, so Judith brought up a good point. If you do this on someone else's piece of software, it is likely illegal. On most pieces of software, you will see a disclaimer when you install it. You know those terms and conditions no one ever reads? Usually that says you may not reverse engineer this software. That's specifically excluding doing this with it. Right? So yes, it is in almost all cases illegal with software that you did not write. Other questions? Is anyone having trouble? Anyone not gotten through the password? Okay. So the last thing we'll look at is actual disassembly. I've made this program very, very easy to change. In fact, we're not even changing the machine code, right? We're just changing the constant the program comes into. Instead of changing it to T when we enter the password, it just starts at T. Right? To actually change the machine code, we normally do what's called disassembly. To do that, I'll just demonstrate this because it's a tedious process to do. And it's kind of a nice visual one as it is, so I think you'll find this kind of interesting. We're going to use what's called IDA. IDA is a disassembler. So we'll wait for this to open up. Yes, it's kind of an acronym. I forget what it stands for, but the D is disassembler. Maybe the A is assembler. I don't know what the I stands for, but yeah, they decided let's name it after Ida Lovelace, and that's the icon they use. Anyone know who Ida Lovelace was? Ida Lovelace. Sarah. Yeah, so Sarah pretty much hit the nail on the head. She was one of the first programmers. She actually wrote programs for mechanical computers. This was back before electricity existed. They used moving parts to compute. Yeah, so she is credited with sort of being the inventor of the modern program. And that's why we use IDA for this program.